Hello 8th class students, as we have completed sound lesson in our previous week, so this week you will get the videos of same exam fear but in a longer version. See, exam fear videos cover all the topics or all the activities which are there in the textbook, so do watch them carefully. Okay, so this chapter is very small, so it doesn't need much attention as per the weightage and as per the number of pages in any comparison. This chapter is very small, so go through these videos and make sure that you understand the topics well, and if you are not able to understand any concept or any topic, then you can raise the issue in the group so that I'll be clearing your doubt personally through Zoom session or through personal meeting in our campuses. Okay.
Introduction. The first day a teacher enters into your classroom. What do you say to the teacher? You all wish a very good morning to the teacher. Suppose, if all the doors in your room are closed, then how can you guess whether anyone is crossing the room? Yes, you can identify it by hearing the footsteps of the person. Objectives. At the end of this lesson, you'll be able to understand that sound is caused by vibrations, know about the musical instruments, identify the sound from musical instruments, understand how sound is produced and propagated by humans, acquire knowledge where the sound requires a medium for propagation, understand the propagation of sound in liquids and solids, analyze the working of human ear, define amplitude, time period and frequency of a vibration, distinguish between loudness and pitch, analyze the audible and inaudible sounds, differentiate between noise and music, understand about the noise pollution and its control measure. Sound is produced by a vibrating body. Sound is a pressure distribution that moves through a medium in the form of mechanical waves. When a force is exerted on an atom, it moves from its rest or equilibrium position and exerts a force on the adjacent particles. These adjacent particles are moved from their rest position, and this continues throughout the medium. This transfer of energy from one particle to the next is how sound travels through a medium. The words mechanical wave is used to describe the distribution of energy through a medium by the transfer of energy from one particle to the next. Sound waves that travel parallel to the direction of the particle movement are called longitudinal waves. However, it is possible to produce other types. Waves which move perpendicular to the direction of particle movement are called transverse waves. After the train crosses the station, if you keep your ear on the rail track, you can clearly hear the vibrations in the rail track. This confirms that sound travels through solids. How is sound produced by human beings? Voice box in human. Sound is produced by the voice box or the larynx in humans. The part which moves when you swallow is known as voice box, which is at the upper end of the windpipe. Two vocal cords are stretched across the voice box. When lungs force air, vocal cords vibrate, producing sound. When the vocal cords are tight and thin, the type or quality of voice is different from that when they are loose and thick. Sound requires a medium for propagation. Place an electric bell in an air-filled jar. You can hear the sound of the electric bell which is ringing. Now suck out the air from the jar using the vacuum pump. As you suck the air out, the sound starts fainting. As all the air sucked out, the sound fully faints. This experiment confirms that a medium is required for the propagation of sound. Sound travels through solids. Ask your friend to hit the bench using a stick at one corner. Keep your ear on the bench at the other corner. As your friend hit the bench, you can hear the sound at the other corner. This confirms that sound travels through solids. Sound travels through air, gases. What you hear is the propagation of sound through air. If there is no air, we can't hear the sound inside the room. We all hear the sound of moving flight. It is due to the propagation of sound through air, gases, which reaches our ear. Sound travels through water, liquids. Place the bell in a beaker filled with water and make it sound. You can hear the sound, which confirms that sound can travel through liquids. Communication between dolphins also confirms that sound travels through liquids as well. We hear sound through our ears. The shape of the outer part of the ear is like a funnel. Sound enters and travels down a canal at the end of which a thin membrane is stretched tightly called eardrum. Sound vibrations make the eardrum vibrate, and the eardrum sends vibrations to the inner ear, and through inner ear it goes to the brain. This is how we hear sound. Amplitude, time period, frequency. Amplitude. Amplitude of the sound is nothing but the loudness or the amount of maximum displacement of the particles while the sound is produced. When the amplitude of the vibration is large, the sound produced is loud. When the amplitude is small, the sound is feeble. Frequency of sound. The number of oscillations per second is called the frequency of the oscillation. Frequency is expressed in terms of hertz. Loudness and pitch. Loudness depends on the amplitude of vibrations. Loudness of sound is proportional to the square of the amplitude of the vibration producing the sound. If the amplitude becomes twice, the loudness increases by a factor of 4. The loudness is expressed in a unit called decibel, dB. The following table gives some idea of the loudness of sound coming from various sources. Above 80 dB, the noise becomes physically painful. Pitch. The two sounds are equally loud. They differ in some way. The difference in sound is due to the shrillness or pitch of the sound. If the sound has high frequency, then it has high pitch or shrillness. If the frequency of vibration is low, then it has low pitch, that is, vibration of drums. Audible sounds. Sounds which we can hear is about 20 Hz to 20,000 Hz. These sounds are called audible sounds. Ultrasonic sounds. These squirrels communicate with each other with a frequency greater than 20,000 Hz. These sounds are called ultrasonic. Dogs, whales have the ability to hear ultrasonic sounds. The ultrasonics are used to take the scan pictures of various vital organs. Infrasonic sounds. Sounds which have frequency less than 20 Hz are termed as infrasonics. Music and noise. Sounds which are pleasant to hear are called as music. Here we have number of instruments which produces pleasing sound. Noise. Sounds which gives discomfort to hear. Such unpleasant sounds are called as noise. For example, when a cup of glass breaks, it produces noise. Noise pollution and its control. Presence of excessive or unwanted sounds in the environment is called noise pollution. The major cause for noise pollution is sounds of vehicles, explosions including bursting of crackers, machines, loudspeakers, etc. Television and transistor radio at high volumes, some kitchen appliances, desert coolers, air conditioners all contribute to noise pollution. Summary. Let us summarize what we have learned. Sound is produced by vibrating objects and it is carried in all directions in a medium. The to and fro or back and forth motion of an object is termed as vibration. In humans, the sound is produced by the voice box or the larynx. Sound needs a medium to travel. The sound cannot travel through vacuum. We hear sound through our ears. Position is called the amplitude of vibration. The to and fro motion of an object is called oscillation motion. The number of oscillations or vibrations per second is called the frequency of oscillation. The frequency of a body is expressed in hertz. Larger the amplitude of vibration, louder is the sound. Higher the frequency of vibration, the higher is the pitch or shrill is the sound. For human ears, the range of audible frequencies is roughly from 20 to 20,000 hertz. The presence of excessive or unwanted sound in the atmosphere is called noise pollution. Major causes of noise pollution are sounds of vehicles, explosions including bursting of crackers, machines, loudspeakers, etc. Plantation on the roadside and elsewhere can reduce the noise pollution.
Introduction.
Hey Pinky, let's go back. I have to study. No, wait. Come, I will show you something. What? Say something loudly. Pinky! Wow, what is this? This is called the echo. Echo? Interesting. Yes, echo of the sound. Do you want to know more about this? Yes. Yes, please tell me. Come, today I will tell you everything about sound.
Objectives.
At the end of this lesson, you will be able to understand the production of sound, understand the propagation of sound, write the characteristics of sound waves, understand the reflection of sound, define echo and reverberation, describe sonar, and explain the structure of human ear. Production of sound. Students, we know that sound is a sensation or a feeling that we hear. Sound is produced with a vibrating object. The motion of materials or objects causes vibrations. Vibration means a kind of rapid to and fro motion of an object. Let us look at some examples of how certain sounds are produced. Human voice. The sound of the human voice is produced due to vibrations in the vocal cords. Animal sound. When a bird flaps its wings, a sound is produced. Bees buzz as they fly because of the rapid movement of their wings. Their wings make the air vibrate, producing a buzzing sound. Musical sounds. Musical instruments produce many different sounds in various ways. Some instruments need to be struck by an object in order to produce a sound, while some instruments, such as a harp or a violin, produce sounds when one or more of their strings are plucked, causing them to vibrate. Propagation of sound. For sound to be generated and heard, it must have three things. They are a source, a medium through which to pass, and a receiver. Let us assume the source is the speaker's voice, the medium through which it is transmitted is air, and the receiver is the listener's ear. When a sound is generated by the speaker's speech, or when an object vibrates, it sets the particle of the medium around it vibrating. The particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. It then exerts a force on the adjacent particle, which gets displaced from its position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches your ear. During propagation of sound in a medium, the particles of the medium do not move forward themselves, but the disturbance is carried forward. So, sound waves are characterized by the motion of particles in the medium and are called mechanical waves. Can you tell the most common medium of sound? Air is the most common medium through which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression. And when the vibrating object moves backwards, it creates a region of low pressure called rarefaction. The compressions are regions of high air pressure, while the rarefactions are regions of low air pressure. Look at this image. It shows a sound wave created by a tuning fork and propagated through the air in an open tube. These are the regions of compression and these are the regions of rarefaction. Sound needs a medium to travel. As sound is created by the vibration of particles, it requires a medium such as air, liquid, or a solid. But how can we prove that it needs medium to travel? Let's see. Look at this figure. Here, an electric bell is suspended inside an airtight glass bell jar connected to a vacuum pump. As the electric bell circuit is completed, the sound is heard. Now, if we slowly remove the air from the bell jar by using a vacuum pump, the intensity of sound goes on decreasing and finally no sound is heard when all the air is drawn out. We would be seeing the hammer striking the gong repeatedly. This clearly proves that sound requires a medium for its propagation. Sound waves are longitudinal waves. A wave in which the particles of the medium vibrate back and forth in the same direction in which the wave is moving is called a longitudinal wave. Longitudinal wave can be produced in all the three mediums: solids, liquids, and gases. Sound waves are longitudinal because the direction of vibration of the particles is parallel to the direction of wave. When a sound wave passes through air, the particles of air vibrate back and forth parallel to the direction of sound wave. Thus, when a sound wave travels in the horizontal direction, then the particles of the medium also vibrate back and forth in the horizontal direction, but parallel to the direction of sound. For example, the waves produced in air when a violin wire is plugged are longitudinal waves. There is also another type of wave called a transverse wave. A transverse wave is the one in which the individual particles of the medium move about their mean positions in a direction perpendicular to the direction of wave propagation. Characteristics of a sound wave. A sound wave can be described by three basic qualities, that is, its frequency, amplitude, and speed. The number of times the wavelength occurs in 1 second is called frequency. It is measured in kilohertz or cycles per second. The faster the sound source vibrates, the higher the frequency. Higher frequencies are interpreted as a higher pitch. For example, when you sing in a high-pitched voice, you are forcing your vocal cords to vibrate quickly. Thus, a high-pitched sound corresponds to more number of compressions and rarefactions passing a fixed point per unit time. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of different pitch. It is usually represented by a Greek letter nu. Its SI unit is Hertz. We know that compressions are the regions where particles are crowded together and represented by the upper portion of the curve. The peak represents the region of maximum compression. Thus, compressions are regions where density as well as pressure is high. Rarefactions are the regions of low pressure where particles are spread apart and are represented by the valley, that is, the lower portion of the curve. A peak is called the crest and a valley is called the trough of a wave. The distance between two consecutive compressions or two consecutive rarefactions is called the wavelength. The wavelength is usually represented by a Greek letter lambda. Its SI unit is meter m. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. It is represented by the symbol t. Its SI unit is second. Frequency and time period are related as nu is equal to 1 upon t. The strength or power of a wave signal is called its amplitude, or the height of the wave when viewed as a graph is the amplitude. The loudness or softness of a sound is determined basically by its amplitude. The amplitude of the sound wave depends upon the force with which an object is made to vibrate. Speed. The speed of sound is defined as the distance with which a point on a wave, such as a compression or a rarefaction, travels per unit time. We know that speed, u is equal to distance upon time, which is equal to lambda upon t. Here, lambda is the wavelength of the sound wave. It is the distance travelled by the sound wave in one time period of the wave. Thus, u is equal to lambda into nu. That is, speed is equal to wavelength into frequency. Speed of sound in different media. The speed of sound depends on the material through which it's passing. It is greater in solids than in liquids or gases because the molecules in a solid are closer than in a liquid or gas. In this table, you can find the speed of sound in different media at 25 degrees Celsius. Reflection of sound. Like light, sound also gets reflected at the surface of a solid or liquid. The reflection of sound follows the same laws as for reflection of light. Angle of incidence is equal to the angle of reflection. The incident wave, reflected wave and the normal lie in the same plane. Sound waves can be reflected by large, hard, smooth, vertical and faraway surfaces, example, walls, buildings and cliffs. Echoes are produced by the reflection of sounds from such surfaces. The sensation of sound persists in our brain for about 0.1 second. To hear a distinct echo, the time interval between the original sound and the reflected one must be at least 0.1 second. If we take the speed of sound to be 344 meters per second at a given temperature, say 22 degrees Celsius in air, the sound must go back to the obstacle and reach back the ear of the listener on reflection after 0.1 second. Hence, the total distance covered by the sound from the point of generation to the reflecting surface and back should be at least 344 meters per second into 0.1 second is equal to 34.4 meters. Thus, for hearing distant echoes, the minimum distance of the obstacle from the source of sound must be half of this distance, that is 17.2 meters. This distance will change with the temperature of air. Echoes may be heard more than once due to successive or multiple reflections. Reverberation. The repeated reflection that results in this persistence of sound is called reverberation. A reverberation is perceived when the reflected sound wave reaches your ear in less than 0.1 second after the original sound wave. For example, a sound created in a big hall will persist by repeated reflection from the walls until it is reduced to a value where it is no longer audible. Let's now solve a problem. A person shouts near a cliff and hears the echo after 5 seconds. What is the distance of the cliff from the person if the speed of the sound, v, is taken as 300 meters second raised to the power minus 1? Given that the speed of sound, v, is 300 meter second raised to the power minus 1. Time taken for hearing the echo, t, is 5 seconds. Distance travelled by the sound is equal to v into t, which is equal to 300 meter second raised to the power minus 1 into 5 seconds is equal to 1500 meters. In 5 seconds, sound has to travel twice the distance between the cliff and the person. Hence, the distance between the cliff and the person is 1500 meters by 2, that is 750 meters. Range of hearing. The average person has a normal hearing range that falls between 20 Hz on the low side and approximately 20,000 Hz on the high side. Children under the age of 5 and some animals such as dogs can hear up to 25 kHz. The hearing range of humans gets worse with age. People lose the ability to hear sounds of high frequency as they grow older. Sounds of frequencies below 20 Hz are called infrasonic sound or infrasound. Some animals like whales and elephants produce sounds in the infrasound range. Frequencies higher than 20 kHz are called ultrasonic sound or ultrasound. Dogs can hear some ultrasound, thus a dog trainer can use an ultrasound whistle to call his dog. Ultrasound is even more important for bats because they rely on ultrasound to see the world. Applications of ultrasound. We use ultrasounds in industries and for medical purposes. Ultrasounds are able to travel along well-defined paths, even in the presence of obstacles. The doctors use a high-frequency ultrasound handheld transducer to scan the mother's abdomen. It is generally used to clean parts located in hard-to-reach places, for example, spiral tube, odd-shaped parts, electronic components, etc. Ultrasounds can be used to detect cracks and flaws in metal blocks. Ultrasonic waves are allowed to pass through the metal block and detectors are used to detect the transmitted waves. If there is even a small defect, the ultrasound gets reflected back, indicating the presence of the flaw or defect. Ultrasound is used for echocardiography. In this, the ultrasonic waves are made to reflect from various parts of the heart and form the image of the heart. Ultrasound is also used to break small stones formed in the kidneys into fine grains. These grains later get flushed out with urine. Sonar. Sonar is the device that uses ultrasonic waves to measure the distance, direction, and speed of underwater objects. The word sonar stands for sound navigation and ranging. Sonar consists of a transmitter and a detector and is installed in a boat or a ship. The transmitter produces and transmits ultrasonic waves. These waves travel through water and after striking the object on the seabed get reflected back and are sensed by the detector. The detector converts the ultrasonic waves into electrical signals which are appropriately interpreted. The distance of the object that reflected the sound wave can be calculated by using echo ranging method. Let the time interval between transmission and reception of ultrasound signal be t, and the speed of sound through seawater be v. The total distance, 2d, travelled by the ultrasound is then 2d is equal to v into t. This is the echo ranging method. Structure of the human ear. The ear consists of three basic parts: the outer ear, the middle ear, and the inner ear. Each part of the ear has a specific role in the task of detecting and interpreting sound. The outer ear is called pinna. It collects the sound from the surroundings. The collected sound passes through the auditory canal. At the end of the auditory canal, there is a thin membrane called the eardrum or tympanic membrane. The eardrum moves inward and outward as the compression or rarefaction reaches it. In this way, the eardrum vibrates. These vibrations are amplified by the three bones, namely the hammer, anvil, and stirrup in the middle ear. The middle ear transmits these vibrations to the inner ear. Inside the inner ear, the vibrations or the pressure variations are converted into electrical signals by the cochlea. These electrical signals are sent to the brain via the auditory nerve and the brain interprets them as sound. Did you know? Heinrich Rudolf Hertz was born on 22nd February 1857 in Hamburg, Germany, and educated at the University of Berlin. He confirmed J.C. Maxwell's electromagnetic theory by his experiments. He laid the foundation for future development of radio, telephone, telegraph, and even television. He also discovered the photoelectric effect, which was later explained by Albert Einstein. The SI unit of frequency was named as Hertz in his honor. Hearing aid. People with hearing loss may need a hearing aid. A hearing aid is an electronic, battery-operated device. The hearing aid receives sound through a microphone. The microphone converts the sound waves to electrical signals. These electrical signals are amplified by an amplifier. The amplified electrical signals are given to a speaker of the hearing aid. The speaker converts the amplified electrical signal to sound and sends to the ear for hearing. Summary. Let us summarize what we have learned. Sound is produced due to vibration of different objects. Sound travels as a longitudinal wave through a material medium. Sound travels as successive compressions and rarefactions in the medium. Sound cannot travel in vacuum. The distance between two consecutive compressions or two consecutive rarefactions is called wavelength, lambda. The time taken by the wave for one complete oscillation of the density or pressure of the medium is called the time period, t. The number of complete oscillations per unit time is called the frequency, nu is equal to 1 upon t. The speed u, frequency nu, and wavelength lambda of sound are related by the equation u is equal to lambda into nu. The speed of sound depends primarily on the nature and the temperature of the transmitting medium. The law of reflection of sound states that the directions in which the sound is incident and reflected makes equal angles with the normal to the reflecting surface, and the three lie in the same plane. For hearing a distinct sound, the time interval between the original sound and the reflected one must be at least 0.1 second. The persistence of sound in an auditorium is the result of repeated reflections of sound and is called reverberation. The audible range of hearing for average human beings is in the frequency range of 20 Hz to 20 kHz. Sound waves with frequencies below the audible range are called infrasonic, and those above the audible range are termed ultrasonic. Ultrasound has many medical and industrial applications. The sonar technique is used to determine the depth of the sea and to locate underwater hills, valleys, submarines, icebergs, sunken ships, etc.
Hear so many sounds in our surroundings in our daily life. When a lion roars, we hear a sound. If we pluck the string of a musical instrument, say a guitar, we hear a sound. Water pouring into a glass, bat hitting the ball, water hitting the rocks, etc. are some of the examples of different sounds. Sound plays a very important role in our life, and most importantly, it helps us to communicate with each other. Have you ever thought about what actually produces the sound? To answer this question, first we need to understand vibration. What is vibration? It is to and fro or back and forth motion of an object. For example, if we stretch this rubber band with one hand and pluck it in the middle, it starts to move back and forth. In short, it starts to vibrate. It is this vibration that produces the sound. Yes, anything that vibrates will produce sound. We will learn more about this in the next video. We know that the voice of adults and children differ. Why is it that the sounds are different? What separates the sounds? Why is it that some sounds are louder than the others? Why are some of the sounds pleasant while other ones are annoying? We will answer all these questions in the coming videos. These are the points that we are going to elaborate on in this series of videos based on sound. Vibrating bodies produce sound, medium of propagation of sound, amplitude, frequency and time period of vibration, loudness and pitch, audible and inaudible sounds, noise pollution and measures to control it. Do watch our coming videos to learn about these concepts and much more. In our previous video, we studied that sound needs a medium for propagation. That is, it requires some medium to travel from one place to another. But how does it really travel through the medium? What happens to the particles of the medium? Let us find out. We now know that sound is produced by vibration. When the object is vibrating, it sets the particles of the medium around into vibration. In the process, the nearest particles to the source gets displaced from their mean or equilibrium position. They start to collide with the particles adjacent to them. The adjacent particles then also get displaced from their mean positions. They in turn do the same to their neighboring particles. This process continues in the medium till the sound reaches our ear. We see that we create some disturbance flowing through the medium. This is the way that sound travels through the medium. We see that particles of the medium are not traveling from the source to the human ear. It is the disturbance produced by a source which is traveling in the medium. The particles are merely oscillating from their mean positions. This disturbance created by the vibrating object in the medium is what we call a sound wave. But what does this disturbance look like? Let us study this with the help of a tuning fork. Here we take air as a medium of propagation. Here we have a tuning fork made up of steel. This shows the initial condition of the air particles of the medium when the tuning fork is in its original position, that is, when tuning fork is not vibrating. When we strike its prong on a rubber band, we start hearing a sound. How does the sound travel through the medium? The two prongs of tuning fork are vibrating. Let us concentrate on motion of one of the prongs first. Say the one on the right. When it's away from its mean position, it pushes and compresses the air particles around it. This creates a high pressure region, also called compression. This compression travels in the medium as a disturbance. Here the density is high. That is, the particles are very close to each other. When the prong comes towards its mean position, the pressure on the right decreases and keeps on decreasing further as the prong continues its motion towards left. This creates a low pressure region, also called as rarefaction. We see that at this point, the compression in the form of disturbance has reached this region. This rarefaction also travels in the medium as a disturbance. Here the density of particles is less. That is, the particles are far away from each other. As it continues to vibrate, we get a series of these compressions and rarefactions. This continuous sequence of compressions and rarefactions is what we call sound waves. Yes, the sound waves travel in the form of compressions and rarefactions. Instead of the tuning fork, if we take any other source of sound, say the speaker, then the sound waves generated by this object will also travel in the form of compressions and rarefactions. Here is one interesting question. Is the sound wave a mechanical wave? Do you know what a mechanical wave is? The mechanical wave is a wave that requires some material medium to travel. And as we know, a sound wave also requires some medium to travel. So yes, it is a mechanical wave. How do you define vacuum? Can sound travel through it? To find the answer to these questions, you have to wait for our next video. See you there. Videos, we have learnt that sound needs a medium to travel. The medium can be a solid, liquid or gas. For example, a doctor uses a stethoscope to hear the sound of our heartbeat. Here the medium of propagation is a solid. Can you think of any example where the medium is a liquid? When you place your ears close to the surface of water, you will still be able to hear the sound from bodies or objects inside. Yes, this is an example where the medium is a liquid. And air is the most common medium through which the sound travels. And air, as we know, is gaseous. What is a vacuum? Vacuum is a space void of any matter. It means that it's a space that does not have any matter. For us humans, it's practically impossible to find or create 100% vacuum. But is there any place which comes close to a vacuum? Yes, the outer space is the closest approximation to a perfect vacuum. This is the reason why we are unable to hear any explosions from stars or planets here on Earth. As outer space is almost a vacuum, the sound from these explosions cannot travel to us. Let us see one experiment. Here we have an electric bell jar. A bell jar is a glass jar whose shape is similar to that of a bell. So we have a glass jar in which electric bell is fixed with the help of a cork. We call it an electric bell because it requires electrical energy to work. This bell is connected to an external battery and key. The glass jar also has a vacuum pump attached to the bottom. When we close the key, the current starts to flow and the hammer starts to strike the gong and continues to do so. We hear the sound clearly. Now we start pumping the air out of the glass jar through the vacuum pump. Is the sound getting louder or is it getting fainter? Yes, the sound is getting fainter. we see that as the amount of air is reducing in the jar, the intensity of sound is decreasing. Although we can see the hammer striking the gong, the sound we hear is very feeble. This is because we create a vacuum inside of the glass jar when we remove the air out. Note that earlier we said that we cannot create 100% vacuum. Hence we cannot remove all the air from the glass jar. So there will be some soft sound that we will be able to hear. We can also perform the same experiment using an alarm clock. Instead of the electric bell, we place ringing alarm clock inside the glass jar. We don't need battery and key in this case. Initially, we will hear the sound of an alarm. But when we try to pump the air out of the jar, the intensity of sound will get lower and the sound will get fainter. Note here that the alarm clock should be chosen in such a way that it can easily pass through the opening of the glass jar. Let us do one more experiment which you can perform at home. Take an empty glass and a cell phone. Keep this cell phone in an empty glass. Ask someone to give you a ring on this phone. What do you notice? Yes, you will hear the sound loud and clear. Now if you put your hands around the open face of the glass like this and try to suck the air from the glass, do you hear the same intensity of sound? Is the sound getting fainter now? Yes, we see as we suck the air out of the glass, the sound gets fainter. And why is that? It's because a new vacuum is created in the glass when we suck the air out from it. We have seen how sound propagates through a medium. When the object vibrates, it creates the disturbance in the surrounding medium, and this disturbance is what we call a sound wave. The wave travels in the medium in the form of compressions and rarefactions. But in which direction do the particles of the medium vibrate? Before we answer that question, we will talk about longitudinal waves. What are longitudinal waves? Let me tell you the fancy definition first. Waves in which the particles of a medium vibrate in a direction parallel or anti-parallel to the direction of energy transport are called longitudinal waves. What does that mean? Before we get to the statement, do you remember what parallel and anti-parallel mean? Parallel would be two vectors like this, and anti-parallel will be two vectors like this. Parallel but in opposite direction. Now coming back to the statement, it means that if the wave travels in this direction, then the particles of the medium also move to and fro along this direction only. So the displacement of particles is parallel or anti-parallel to the direction of the propagation of wave. Is sound wave a longitudinal wave? Take this example and try to find out. Yes, sound waves are indeed longitudinal waves. We see this in this example that the particles of the medium are vibrating in the direction of propagation of wave. Sound waves are also called pressure waves. Can you tell me why? It is because the sound wave consists of the repeating pattern of high pressure regions called compressions and low pressure regions called rarefactions through the medium. But wait, hold on. Are there waves in which the displacement of particles of the medium is not in the direction of propagation of the wave? The answer is yes. Let's see one example in which the propagation of the particles is perpendicular to the direction of propagation of the wave. Take a string with one end fixed to the wall. This end is fixed at the wall here, and this one is in your hand. We see a wave when we give the string an upward jerk from this end. What do you notice here? In what direction are the particles of the string moving? Up and down, right? And what about the direction of the propagation of the wave? It's moving to the right. Let me repeat it once. The particles in the string are moving up and down while the direction of propagation of the wave is towards the right. the particles are vibrating in a direction perpendicular to the direction of the wave. Such waves are called transverse waves. So are sound waves transverse waves? The answer is no, and it's because the particles of the medium are vibrating in the direction of propagation of wave. Here is a quick recap of what we did today. We saw that longitudinal waves are the waves in which particles of the medium vibrate in a direction parallel to the direction of motion. Sound waves are longitudinal waves. Sound propagates through the medium in the form of high pressure and low pressure regions. Hence, sound waves are also called pressure waves. And at the end, we saw what transverse waves mean. They are waves in which particles vibrate at right angles to the direction of its propagation. In the next video, we will understand more about the propagation of sound waves. See you there. From our past videos, we know that light follows law of reflection after being incident on a surface. Just like the light waves, sound waves also get reflected from the surface of a solid. They also follow the same law of reflection. Let us see what that law is. Say we have our source which is emitting sound, and assume one of the sound waves strikes the surface at this point. Let's draw a normal to this surface. Normal is nothing but the line which is perpendicular to the surface at the point of incidence. Now this wave will be reflected from the surface. The law of reflection tells us that this sound wave will be reflected back in such a way that the angle of incidence I is equal to the angle of reflection R. Also, the incident ray, the reflected ray, and the normal will all lie in the same plane. What if a wave is incident perpendicular to the surface? Well, in that case, the reflected sound will travel back in the opposite direction along the same line. Here is one demonstration that you can perform at home to verify these laws. Take two small hollow cylindrical shaped objects which are open from both ends. Two straight hollow pipes would suffice. Place them on the table like this near the wall. We also need to make sure that the table is covered with a white cardboard paper before keeping the pipes on it. Place a running clock near the open end of the pipe facing you. And now keep your ear near the open end of the other pipe. Did you hear the sound of the ticks coming from the pipe? Adjust the pipes a little until the sound is clearer. At one point, it will be very clear. This is an example of reflection of sound. Yes, you are hearing the reflected sound. The sound wave from the clock passes through this pipe and is incident on the wall. It gets reflected and passes through the other pipe and enters your ear. You will notice that these two angles are approximately equal. The angle of incidence will be equal to the angle of reflection if we ignore any human errors. Echo is another example where one is able to hear the reflected sound. What is an echo? The repetition of the same sound again and again is what we call an echo. Where do we hear an echo? Well, we usually hear it in empty spaces bounded by at least one tall surface. For example, when we're inside a large canyon or when we're shouting in a deep empty well from above. If we clap in an open space standing against a tall wall, we will also hear the sound of our clap again and again. Why does it happen? The sound from a clap travels in all the possible directions. When it collides with the obstacle, it gets reflected back. These reflected sound waves then travel towards us and we hear faint repetitions of our clap again and again. But hold on, are there any conditions? Or will we hear an echo in any and every case? Yes, there are a few conditions. The echo depends on the temperature of the surroundings and the distance between you and the point of reflection. Let me give you an example. Assume that the temperature of the surroundings is approximately 22 degrees Celsius. At this temperature, the distance between you and the wall has to be at least 17.2 meters for you to hear an echo. Only if it's equal to or greater than 17.2 meters, you may hear an echo. Otherwise, you wouldn't. But why did we have this condition? What if the temperature is different? What if the distance is less than 17.2 meters? Are there any other conditions apart from temperature and distance? We will answer these questions in our next video.